the last part of this part 2. Okay, just 1 hour, and then we'll do tutorial, right? Okay, so today I will continue on the DC analysis. So this part you have done on the mathematical method. Okay, you have seen 3 types of circuit configuration: fixed bias, emitter stabilized bias, and voltage divider. Okay, so you have done the mathematical method for all these 3 circuits. Okay, so today we'll do the, I will introduce to you the how you solve this circuit using graphical method. Okay, same like diode where you have the graphical method, you have to draw the load line and everything. So in here, BJT also you have to draw the load line. Okay. All right, so BJT load line. So this is, of course, when we talk about load line, so there will be a Q point. Okay, so same like diode where you have Q point at the center of the load line, where that is determine the active region of your Q point. Okay, so why do we determine this active region? Because BJT works as amplifier, okay, best as amplifier. So the region where it amplify the signal in very stable and with a high stability is during at active region. So what is the operating point? It is a quiescent point or Q point. So the biasing circuit can be designed to set the device operation, okay, and any of this within the active region. Okay, so the Q point often depends on the intended use of the circuit. Okay, so if you want to use it as an amplifier, your BJT circuit as amplifier, so your Q point must fall in the active region, which means in the center of the load line. Okay, so the operating point of amplifier to state the values of the current, again ICQ and also VCEQ. Okay. In the last class, okay, I have shown you. So this is, for example, this is the circuit given. Okay, so this is the transistor must be amplified correctly. Okay, so this is your IV characteristic for BJT at the output. Okay, as you can see, for example, this is your circuit, which is the fixed bias circuit, okay, where you don't have resistor at the emitter. Therefore, this is a fixed bias. Okay, and then you have voltage supply, okay, at the input and also at the output. Okay, usually the voltage supply is same. Okay, where you have the same VCC here and same VCC here. All right, so this is the input part from base to emitter. So this is the output part from collector to emitter. All right, so same like diode. So you will be given the curve. Okay, this one is represent the IV characteristic at the output. Okay, as you can see, the current is collector current, IC current, and also the output is VCE voltage. Okay, here the IC current and VCE voltage. So this is the characteristic for the current characteristic for the BJT, where you have the collector current increase with the increment of IB. Okay, why? I think you have familiar with this. So your IC is approximately equal to your IC is approximately equal to IB. If you have increment in IB, therefore you have increment in IC. So all this depends on your beta value as well as your IB. So this is the output characteristic of the BJT at collector to emitter. Okay, so as the voltage increase, VC increase, so the current is actually saturate. All right. So from here, as you can see, there are three regions actually. Okay. So one near the y-axis, there is a saturation region. So this saturation region means that you have voltage here is 0. Okay. As you can see, at saturation here, so at this point is IC is saturate. Okay, this is IC saturation. During this case, VCE equal to 0. Okay, y-axis equal to 0. And the other one, okay, this is the first point, the saturation region. The second one is cut-off region. Okay, where here your IC is approximately equal to 0, and you have your VCE equal to the maximum VCE. Okay, so maximum VCE is equal to the VCC. What is VCC? VCC where you apply the power supply here. All right, so you have one saturation region, two cut-off region, and the third one is actually the active region. Okay, third one is your active point. Okay, where your Q point fall at active region. Okay, where does the active region? So usually active region fall in between saturation and cut-off. Usually at the center of this load line. Okay, at the center of this load line. So it could be Q2 or it could be between Q1 and Q2 or between Q2 and Q3. All right. Okay, so there are various operating point within the limit of operation transistor. So this one, Q point A, for example, this point Q point A. So this is not suitable for transistor to operate because here the voltage is 0, the current is also 0. All right. So for example, if you have Q point at B, okay, here, okay, so this is the best operating point, or usually this one we call it as a active region, okay, where the Q point fall in active region point. All right, so this is the best where a transistor will have the largest possible voltage and current, and also transistor will works best as an amplifier. Okay, so the another one is Q point C. So this is concerned on the non-linearity due to the IB curve is rapidly changed. So this is too close to the 0, and this is at the center of the IV characteristic. So Q point B is usually the best operating point. Okay, so like I said, you have saturation region, cut-off region, and this one is active region. Okay. All right, so at this saturation point, so where you have this is the IC max, or usually we call it as IC saturation. All right, and also you have this one at this cut off point. Okay, at this cut off point, so usually they call it as a VCE max. Okay, VCE max, or equal to the VCC. Okay, so with a good Q point, your transistor or your BJT can amplify a good signal. Okay, at the collector of the and it has swing smoothly without exceed the limit of operation, either saturation or cut off. And if we apply too high AC voltage to the base, okay, to the base terminal, would result in driving the collector current into saturation or cut off. All right. So for example, this is your BJT where it has been drawn as an amplifier. So we know that BJT can where you can develop or design BJT as amplifier. So inside here is your BJT circuit, for example, voltage divider circuit. So this is the amplifier symbol. So for example, if you have a larger output has the same shape as input except at this inverted. Okay, so for example, you have this input and your output being inverted, means this one has negative voltage gain. Okay, so if this one, the larger input, but it being clipped by the cutoff, which is your Q point is not at the center of the active region, okay, therefore you might get this non-linear operation where your output might be clipped, okay, due to the clip off, or your output might be clipped at the negative voltage, at the negative cycle due to the saturation. Okay, this is happen when your Q point fall near the cutoff region, and this is happen when your Q point fall in near your saturation region. All right, so DC load line, okay, this is the red color here is your load line. So given, for example, this IV characteristic, okay, so this curve is given where you have your IV characteristic of collector versus VCE. So this given, okay, what you should do is you have to draw this DC load line, the red color. Okay, the red color one. So how do you define your Q point? Your Q point must fall into this load line, right? So how do you get this load line? You need to have 2 points, like I said in the previous class for BJT. So you need to have 2 point, okay? 1 point. Okay, how to draw the load line? So you need to have 1 point at first point at y-axis. Okay, second point is at x axis. Okay, so your point must be here, 1 point here and 1 point here. Okay, how you get this first and second point is by using it's either this is the saturation point where IC equal to the saturation. So in your circuit, you have your circuit, for example, this one, fixed bias. Okay, so you're concentrating at this output. So what is your KVL at this output? So your KVL will be, so what is your KVL here? So your KVL here is VCC, okay, minus ICRC minus VCE equal to 0. Okay, for example, this is your Q point. So if I write again your Q point here, okay, so your Q point KVL at output loop, okay, is equal to the VCC minus ICRC minus VCE equal to 0. All right. So like I said, you need to have 2 point at y-axis and x-axis. Therefore, what you should do is same like you have done in diode. Okay, same like you have done in diode. Okay, at x-axis equal to 0, what is the y-axis value? At y-axis equal to 0, what is the x-axis value? Okay, therefore, this is what they did. Okay, for example, here in this case, when VCE equal to 0, IC, okay, from this equation, okay, IC is equal to VCC over RC. Okay, for this one, when IC equal to 0, okay, when IC equal to 0, your VCE is equal to the VCC. For example, here, so your VCE, okay, doesn't matter. Okay, we'll look at example. So in this case, it would be VCE equal to the VCC. All right, so you have 2 points. Okay, one at y-axis, another one at x-axis. All right. So load line analysis, okay, for this one. So DC load line can be drawn at the output IV characteristic, okay, like I said. So the line connecting each separate Q point, okay, you need to have two points at y-axis and x-axis in order to draw your load line. And at any along the load line, okay, values IV, IC, and VCE can be picked off from the graph. All right. So these are the steps. Okay, so first step is you need to write your KVL at the output loop. Okay, so this is first step, KVL at output loop. So since this circuit is fixed bias circuit, okay, where you don't have your RE value here. Okay, as you can see, you don't have resistor at RE here. Therefore, your KVL is quite straightforward, okay, which is equal to VCC minus ICRC minus VCE equal to 0. All right, so this is your Q point. Sorry, this is your KVL. Okay, and then what happened next is to find two points, okay, at IC equal to 0, okay, VCE equal to the VCC. So this is your first point at x-axis. Okay, when VCE equal to 0, okay, when VCE equal to 0, therefore IC is equal to the VCC over RC. Okay, so this is your second point at y-axis. All right, so first step, okay, write the KVL. Second step is to get all the points, okay, 2 points, okay. Okay, third step is to draw your load line. Okay, like I said, given the IV characteristic, you need to draw your load line. Okay, so now here you already have your load line, okay, where you connect between this first point and second point. Okay, now your Q point, okay, must be fall in between this line. Okay, on this line, okay, must be fall on this line, but we don't know. Okay, in this case, they said that for this case, maybe they already know the IB. Okay, like for example, this IB is usually has value. So this is IB1, IB2, IB3, and so on. Okay. All right, so on. So if you already know, if let's say in the question said that IB is equal to the 60 microampere, so you need to find where is your 60 microampere. So your Q point must be fall in between it. For example, 60 microampere is equal to the IB3. Therefore, your Q point is here. Okay, fall here. Okay, so let's we look at the example later, so you will be much clearer. Okay, so level IB change. Okay, if IB change, okay, so as your Q point also change. Okay, so Q point will move up either upward or downward. Okay, so this is case 1. Okay, what about if you have fixed VCC? Now your RC is changed. Okay, so VCC is fixed. Okay, we know that at this particular point, okay, at this particular point is equal to the VCC over RC. Okay, VCC over RC. So this one. Okay, VCC over RC. So if let's say RC increase or decrease, okay, your load line will either shift downward or upward. Okay, if your RC is increased, therefore your load line will drop downward. Okay, if your RC decrease, therefore your load line will move upward. All right, so this is second case. Okay, what about third case? Okay, if both are varied, okay, RC varied, VCC varied, so you could imagine that your Q point has the same slope, but then shift to the left or to the right. Okay, so you don't have to memorize this. You just have to understand it. Okay, so you know that at this, if this is your initial Q point, Okay, given it is equal to the VCC over RC, and you know at this point is VCE max equal to the VCC. Therefore, if they said RC is increased or decreased, then you have to imagine yourself. Okay, if RC is increased, therefore you expect that this point will drop to here. Okay, so that's how you do it. All right. Okay, let's take a look on the example. Okay, so this one. All right, so this is example, okay? So given this IV characteristic, okay, so this is your IV characteristic, IC versus VCE, and also given your fixed bias circuit with all the values here, okay? So you know that Q point, okay, they also find the new value of Q point if beta is changed to 150. Okay, now let's do first on the Q point first. Okay, so let's take a look here. Let me do. All right. So given 12 volt, 560. So therefore you have wait, let me. Okay. All right, so this is your circuit. Okay, so first step, like I said just now, you have to write the KVL. Okay, write the KVL output loop. So where is your output loop? From collector to emitter. So I think you have already familiar with this. So draw your output loop of this circuit. Okay, of this circuit. Okay, I need to one more time. I need to copy. All right. So if you want to draw your output loop, so you have, so first step, okay, step 1, okay, KVL at output loop. All right, KVL at output loop. Okay, so if you want to draw, you need to get your equivalent circuit at the output loop. Okay, so this is fixed bias circuit. I think you have familiar with this. So draw your BJT. So this is base, this is emitter, this is collector. So at collector, you have RC, which is 560 ohm. Okay, and then you have your VCC plus VCC, and then negative VCC will go to the ground. Okay, so VCC 12 volt here. All right, so this is your output loop. Okay, so don't forget that you have here is your IC, and you have voltage junction here is VCE. All right, I think you all have already familiar with this. Okay, so write the KVL. So KVL will be VCC minus ICRC minus VCE equal to 0. All right, so this is your very first step. Okay, your second step, okay, look at the question. So you need to have 2 points, okay, at y-axis and also x-axis. Okay, now let's do the second step. Okay, so step 2, get the point. Okay, so step 2, sorry. All right. Oh my God. It doesn't matter. All right. So at VCE equal to 0, IC is equal to what? IC is equal to VCC over RC. So you know that your VCC is equal to 12, okay, divide by RC, 560 equals to, can someone calculate for me?
21.4 milliampere.
All right, 21.4 milliampere. So determine the
Doctor,
value of Q point. Yes?
doctor, I think it's 0.0214.
What?
Like 12 divided by 560, right? So it's supposed to be 0.0214.
I don't know. Can you calculate for me, everyone?
Like 0.0214. My calculator says so.
I
In
see that's
milli,
a
maybe?
transfer in milli.
In milli?
Yeah, 21.4 milliampere.
21.4 milliampere. All right. Okay. Thank you.
And now
So
it's okay.
again, what?
Now it's okay, doctor.
All right. Okay. So at IC equal to 0, therefore your VCE is equal to the VCC, which is 12 volt. Right? So now you have first point and second point. Okay, so look at the question. So the question said, okay, can be solved using DC analysis and also DC load line. So DC analysis, do you still remember what is DC analysis? The one that you have done in the previous lecture, where you analyze the circuit, the input loop and output loop. Okay, and then you get the IBQ and also the ICQ. Okay, now I'm solving the second one, which is the DC load line. All right, the DC load line. Okay, later you can do the DC analysis, which is the mathematical method where you analyze the input loop and also the output loop to get the IBQ and ICQ, and then you compare with your DC load line. So now I'm concentrating on the DC load line. Okay. Okay. So now you have 2 points. All right. So this is your first point. Okay. So this is your second point. Okay, so let's draw. Okay, so first is 21.4 milli. Oh, we cannot get it top. I don't like this. Okay, so 21. So 21.4 milli is for here. Okay, for here. Actually, what you can do, so you can do is either use replace
Madam,
it. Yeah.
why the circuit is do not same with example 4?
Not same, eh? 1K. Oh my God. When did I get
I
this?
think you
I use the different value, isn't it?
I don't know lah, maybe.
Yes, doctor.
Oh, I copy this different one. Where did I copy here? Sorry. Sorry. Oh,
It's okay, doctor.
where did I copy it? It's because I just copied.
Just now I confused why over the
Sorry.
560 ohm.
Okay. Yeah, see? I copy this the same thing. Oh, I know. I know why. So actually I changed the value like this. Okay. Sorry about that. Okay, so I have 1K. I copied the different one. Okay. 50 milli. All right, doesn't matter. Okay, let's change the value. So 1K here. So this is 1K. Oh, I cannot. So this is the same one, right? 1K, right? Am I right?
Yeah.
All right.
Yes, doctor.
So this is 1K ohm and 12 volt.
12,
All right.
12 milli,
Okay, can someone calculate for me, please?
12 milliampere.
12 milliampere for the first point, second point, 12 volt. All right, thank you. All right, thank you for just now. You realize it means you're not sleepy. So first point, 12 milli. All right. Second point is 12 volt, which is here. All right, can you see? So you have 2 points, okay, at 12 milli and also 12 volt. Okay, so now is to draw the load line. Okay, I use ruler with me right now. All right, so you have there, that is your load, your Q point. Okay, your Q point is there. Okay, all right. So, sorry, there is your load line. So this is your load line. Okay, so so this is your load line. So your Q point must be fall in on the load line there. So how to determine your Q point on the load line? You need to get your IB. Okay, can you get your IB from here? Can you get your IB from here?
Yes, sir.
From here? Can you get your IB?
Yes.
Okay, so how?
IB equal to beta
No, you
beta
didn't have your
IC.
IC yet.
equal to beta IB.
But you don't have your IC yet. That is this IC, which is 12 milli, is not equal to the ICQ. Okay, so this is just a point at the saturation. Okay, in order to draw the load line. Okay, so can you get your IB from here? Can, right? How? Because you have your input loop here. Okay, so you have 200K here, and also you have your voltage here, 12 volt. Remember? Hello?
Yes,
And
sir.
you have your
The
VBE here. So can you find your IB?
generator.
Yes,
Yes, sir.
can, right? From the input loop. From the input loop. Okay. So from input loop, okay. So your KVL is 12 minus IBRB, okay, minus VBE equal to 0. Okay, therefore, your IB is equal to 12 minus 0.7 over 200K, which is equal to, can someone calculate for me?
Dr. 0.0565.
Can you give me in micro?
56.5 micro.
All right, 56.5 microampere. Okay, so your IB, so where does your IB? Okay, so look at carefully here at the IV characteristic here. Okay, so this is your load line. Okay, so this is, as I said, so this is for different IB. Okay, so from 0 microampere, 20 microampere, 40 microampere, 60 microampere, 80 and 100. So now your IB here is 56.5. Okay, 56.5. Where does it fall? It is in between this 40 and 50. All right. So I can say that your in this case, I will say that my IB is around this region. So it's about 50. So this is in between this is 50. Therefore, 56 is I think this is here. Okay. So this is at 56.5. Okay, roughly like that. Okay, so your Q point is for at this 56.5 microampere, which is here. So this is your Q point. Okay, so this is your Q point. All right. So anyone have question regarding this? How you get the Q point? So I want to use different color. So this is your Q point. Okay. So any question before I move forward?
No
Are you all
questions.
clear about getting the load line and Q point?
Yes, sir.
All right. Okay, great. Okay, so from the Q point, what is your objective? Okay, so same like DC load line for diode. Okay, when you find Q point, you want to get your IDQ and also your VDQ. Okay, but in BJT, okay, when you get your Q point, okay, you want to find your what? In this case, it is VCEQ. Yeah. Okay, and also your ICQ here. Okay, so this is your objective. So in this case, your VCEQ is about 4.1, about like that. Okay, if you draw properly. So ICQ, okay, it's about 8 milliampere. Okay, 8 milliampere. Okay, that's how you do it. Okay, so you can also straight away do the analysis for the input loop. Okay, here. Okay, for last time in the previous lecture, you solve the input loop and also the output loop in order to get the IB. Okay, and then you solve the output loop to get your IC. Okay, that is mathematical. But in load line, okay, you just have to usually you don't have to do this. Okay, the question will give you what is IB. Okay, then you straight away get IB from the load line here. Okay, but this time they didn't give you IB, so you still can get the IB. Okay, where you solve the input loop, get the IB, then you can get your Q point. Okay, so from here, if load line, you don't have to do your output KVL analysis or what so not. Okay, so you get from the Q point here. So your VCEQ is 4.1 volt and ICQ is 8 milli. Okay, so that's how you solve using second method, which is DC load line. Okay, so the question usually will state that you have to solve using a DC analysis. Okay, DC analysis is mathematical. Okay, and DC load line where you have to draw your load line like this. Okay, all right. Do you have any question regarding this?
No, doctor.
All right, great. Okay. Okay, so actually I have also solved the this example. Okay, so this is the DC analysis using mathematical. I think you have familiar with this. Okay, although I didn't draw everything the circuit like what I have done in the previous class, but I believe you all already know. So this one is solved by using the input loop. Okay, KVL at input loop. All right, so this one is KVL at output loop. Okay, so once you get your IV, okay, you can get your IC, okay, from the beta, okay, and then VCEQ, you will get straight away like this. Okay, as you can see, from here. So this is quite different because the ICQ is about 5.65, but the Q point here, VCEQ 6.35. Okay, but the one you get here from the load line, it's about 8 milli and 4.1 volt. There, because this question is not designed perfectly. If it is simulated and designed perfectly, you will get like almost similar Q point. Okay. All right, so that's how you do it. So this is the DC load line where I have done it in the previous slide. So this is also the solution. So almost same, okay, like I drawn just now, okay. So you get ICQ 8 milliampere and VCEQ 4 volt. Okay, so that's how you do it. So do you have any question, okay, on the DC load line especially? I'm not worried about this DC analysis because you can solve it yourself, okay, where you solve the input loop and output loop. But the DC load line, do you have any question? No question. All right. Okay, so let's take a look on the example 5. Okay, so this one. So this is more on, so I am expecting that your test 2, where you have BJT question, so you have quite pretty similar to this kind of question. Why? Because it is very hard for us, okay, to give you draw DC load line like this, because this is online examination. I don't know whether I'm not sure whether it's going to be online or face to face. I'm not sure. If it is online, okay, therefore we will give you some sort of this question. Okay, if it is not online, then face to face, then it will be easy for you to draw the load line, because all the answer sheet will be given. Okay, but if it is online, then it will be something to do like this. Okay, where you have to do something reverse. Okay, given the load line. Okay, given the load line. Okay, by considering the fixed bias circuit. Okay, imagine this circuit is not given, so I just drawn this circuit for you in case you forgot what is fixed bias. So this is a past test question where this one is not given. This is not given. Just give you this, okay, the load line, and also this question. Okay, by considering fixed bias circuit, you have to know what fixed bias circuit, what is it looks like. Okay, but this one solution, I put it the circuit like this. So the circuit fixed bias where you don't have the resistor RE. Okay, determine, so from here, determine the value of VCE, RC, RB, and also I think VCC from this question. Okay, so it doesn't matter. Okay, so you need to determine all these resistor value. So it's like a reverse question, more on design question, where you do a reverse solution. Okay, so do you have any idea how to solve this for the first step? Any idea? What would be the first step?
BCE.
Wait, let me get one more. One more. Okay, I need to copy this first. I need to copy both of this to here. All right. Okay, what will be the first step from here? Okay, so you need to find this RB, okay, RC, and VCC. Okay, now you already know your Q point. Okay, so from your Q point here, you already know. Okay, so first thing is you at least you already know this 2 point. Okay, at here and here. Okay, how do you actually get these 2 points? Okay, from the KVL, right? So I want to draw the circuit. Okay, so this is the circuit. So I need to draw the input loop and the output loop. Okay. Okay, so this is your RC. So this is your VCC, and this is VCE. This is IC. Okay, so KVL here. So KVL at output loop. So you have VCC minus ICRC, okay, minus VCE equal to 0. Okay, now, okay, how do you get these 2 points at y-axis and x-axis is when IC equal to 0 and VCC equal to what? VCE equal to 0 and IC equal to what, right? So for example, if you take this, okay, at IC equal to 0, okay, when IC equal to 0, okay, meaning that you get something point at this point, right? IC equal to 0 means that at this point, okay, which is here, okay. So when IC equal to 0, this is actually VCE equal to VCC. Okay, so what is this VCE? So this is the VCE max from the circuit, from the load line. How much is this? What is the value for the VCE max here when IC equal to 0? Yes, 40. Therefore, here is 40 volt, which is equal to your VCC. Okay, so from here, you get that this value 40 is your VCC, which is equal to the 40 volt. Okay, you have the value now for the VCC. Okay, next, okay, you have make use of this point. Okay, now you have another point here. So this point is at IC maximum, where this point fall at y-axis. Therefore, at this point, who equal to 0? VCE equal to 0. Okay, so for this case, okay, for example, at VCE equal to 0, okay, IC is equal to the VCC over RC. Okay, from here, you know that this is your IC. Sorry. So this is your IC maximum. How much is your RC maximum here?
15.
Yes, 15. Thank you. So it will be, this here is 15 milli. Okay, don't forget this is in milli. Okay, all right. So it's equal to the VCC. You have got the value VCC,
40.
which is 40, correct? Okay, and RC. Can someone calculate for me what is RC value?
2.67 kilo ohm.
2.67 kilo.
All right. Okay, 2.67. So you have your value here, 2.67 kilo ohm. All right. So what's left now is your RB. Okay, RB. So this is more on design question. So everything you take out from the load line. Okay. So now is to get your RB. Okay. So how to solve the RB? Of course, from where? From the input loop. Okay, so you have the RB and you have here your VCC. This is go to the ground. Okay, this is your VBE. Can you get your RB from here, student? Can you get RB?
Yes. Yes.
Yes, from the input loop. Okay, how? VCC you already know, 40 volt. Okay, VBE you know. Can you calculate your RB? Okay, how do you get your, okay, so now KVL at input loop. Okay, let's do together. KVL at input loop. So what is the KVL at input loop, student? Hello?
40 minus
Okay, yes, VCC minus IB.
RB
RB
Yeah.
minus
minus
VBE.
Anything else, you don't have RE, therefore equal to 0. Okay, so where do you get your IB here? Where to find your IB?
From the load line.
Yes, correct. IBQ from the load line. Okay, how much is this? So let's take a look together. So can you guess not guess, I mean like
So 17 micro.
about
millimeter.
70 micro. Okay, about 70 micron. Okay. Right. So is equal to the 70 microampere from load line. Thank you. All right. Therefore, can you get your RB? Can, because you have VCC, you already have your IB, VBE you know. Can you get your RB? Of course, definitely you can. Okay. So it's equal to the VCC minus VBE over IB. This is equal to 40 minus 0.7 over 17 micro. How much the value?
Two point three one one.
Again, 2.3,
11.
2.3,
1.
1.
That's right.
Kilo, mega,
Mega.
Mega.
mega. Okay. All right, great. Okay, so you have the value here, 2.31 mega ohm. All right, so this is exactly past test question would be. So this is I took from the past test question. Okay, so this is how you do it. Okay, so this kind of question we call it as a design question. Oh, sorry, I need to plug in power supply. Okay. Okay, now I'm good. Okay, so this is a design question. We call it as a design question where you should, you design means you determine all the resistor and voltage value with given load line. Okay, with a given load line. All right, now you have done this part. Okay, so any question regarding this? So look at the question, determine the value of VCE, RC, and RB. So actually this one is not VCE, so determine VCC, RC, and RB. All right, so you do have any question? Actually, this circuit is not given, okay? So just they gave the sentence fixed bias, okay? So you need to know that fixed bias, how it looks like, okay? Remember that fixed bias doesn't have resistor RE, okay? So this is a solution. Do you have any question before I move forward?
Alright then.
No. All right. Great.
Doctor,
Yeah.
the value of IBQ they give us,
Where? Again? One more time?
the value of IBQ.
Uh-huh.
We took it approximately at 17 microamperes, right?
Yes,
Do they
correct.
give us the exact one, or we have to guess?
Sometimes they give us the exact one. Sometimes you have to extract from here.
By
Yeah.
guessing?
You guessing, but logic guess.
Okay.
Okay. So it must
Alright.
be like more than 15 lah. More than 15. Okay. All
Okay.
right. Okay. All right, great. Okay. Okay, so of course, I put the solution here so you can take a look later. Okay, so this is on the BJT load line. Okay, that's it for today's lecture, but we will do the tutorial. Okay, so if you have no question regarding the BJT, so I think I will stop recording. Okay, and then take 5. Okay, we'll start with the tutorial. Are you all okay?